Good morning, Mr. Fauzi. I'm Leung Zhiqi. Today, my friends and I would like to present about the production of sodium hydroxide by using the electrolysis method. Our main objective is to produce 100 metric tons per year of sodium hydroxide using sodium chloride and water. Chlor-alkali electrolysis method will be used in this process to let the ion exchange happen between the sodium chloride and water in order to produce the sodium hydroxide. The raw material that we choose are sodium chloride, sodium sulfate, which is the impurity in sodium chloride, and water. The another raw material is barium chloride, which is used to remove the sodium sulfate in sodium chloride. In this process, there are four main steps. The first step is to dissolve the sodium chloride into water and heat it until exceeds 100 degrees Celsius to ensure it totally dissolved. And the second step is to add the barium chloride into the mixed solution to remove the impurity in the sodium chloride. The third step is the electrolysis reaction. The next step is separate the sodium hydroxide from other products, which are hydrogen and chlorine gases. And now I will pass to Chan Wen-jing to explain the next part.
For process flow diagram selection part, we have chosen three process paths as our reference for our simulation design. In the first process path, we can see that the separation process is very important to remove the impurities from brine solution, and hence, the separator is one of the main unit operations in this process. In our simulation design, we assume that the impurities is sodium sulfate, and it is removed by adding barium chloride in a separator. In second process path, electrolysis process occurs at the electrolyte. From the figure, it shows that the main product sodium hydroxide is produced, and the byproducts are chlorine and hydrogen gas. Chlorine gas is produced at the anode, which is positive electron, while hydrogen gas and sodium hydroxide is produced at the cathode, which is negative electron. Therefore, electrolyte is the main unit operation in this process for a reaction to occur. Third process path, separator and cooler are the main unit operation. Separator is used to separate sodium hydroxide from the mixture, and sodium hydroxide is cooled down and sent for storage. To sum up, we have to include this main unit operation in our process design in order to simulate the process of production of sodium hydroxide.
Okay, there are few assumptions was made in this primary simulation. First, the free package we use is fan ambition. We assume the mass flow, composition, mass fraction, temperature, delta P in the stream were applicable. There are two inner streams was introduced in this reaction. First is with sodium chloride and sodium sulfate, and another one is with water. The sodium sulfate is added as impurities in these reactions, and the flow mixed together in mixture and flow to the heater. The heater is used to heat up the product into 1 and 5 degrees Celsius to make sure it is in liquid form. If not, it will return to crystal structure. For the separator ones, the barium chloride is introduced in these reactions. It is used to precipitate the barium sulfate. The equation happen in this reaction is sodium sulfate plus barium chloride plus sodium chloride plus barium sulfate. After that, it will go to the electrolyte. The electrolyte is used to produce sodium hydroxide, and the sodium sulfate is produced as byproduct in these reactions. So the equation in the electrolyte is sodium chloride plus water will produce sodium hydroxide, chlorine, and hydrogen. Then it will flow to the cooler and the mixture. And a recycle stream is introduced to recycle back the sodium chloride that are not react in the reaction. And then for the mixture, it will go to the separator tool. The separator tool is used to separate sodium hydroxide from water, sodium sulfate, chlorine, and hydrogen. For the mass and energy balance, we choose to calculate for separator tool. We use the equation of mass in equal to mass out. So we calculate the mass flow in times composition mass fractions equal to mass flow out times composition mass fractions. The inlet stream is for the separator 2 is S10C and the outlet stream is S11 and S12. So for the water we calculate for the error is 3.4x times 10 power of negative 3%. For sodium hydroxide, we calculate the error is 0.013%. For the chlorine is 0.82%. For the hydrogens, we calculate is 44.58%. So for the overall, the error is 0%. So for the energy balance, so we calculate from the equation Q plus W equals to enthalpy plus kinetic energies plus potential energies. So calculate from the equation Q plus W equals to enthalpy plus kinetic energies plus potential energies. So assumes there is no work involved in the system, there is no acceleration of fluid occur, and there's no elevation of the flow. So if cut off the equations, and then we will get Q equal to enthalpy and equals to molar flow times molar enthalpy. So the calculations we will get negative 82.945 kilojoule per hour. This is for manual. For the simulations, we calculate heat out minus heat in, and we will get negative 50 kilojoule per hour. And the error we calculate is 39.72%. Okay, that's all for my parts.
Hello, Mr. Fauzi and my group mates. My name is Kuiki. So I'm presenting for the result and discussion part in the group assignment. After carrying out mass balance, we found that the result was acceptable as the error percentage for most of the component is small. The value calculated by the calculator will have minor difference due to different significant value was taken. Take hydrogen gas as a number. We calculated the mole fraction for hydrogen gas is 4.15 times power of negative 6 compared to simulation shows that 6 times 10 power of negative 6. The value is very small. However, a small difference can give a huge error percentage. That's why the error percentage for the hydrogen is 44.58%. So besides that, rounding up the figure will also affect the result calculator. This was due to the simulator or computer was able to take decimal point more than 5 or equal to 5, while we only take decimal point up to 6 in calculation. So in fact, higher decimal point taken for calculation can increase the accuracy and also improve the similarity between manual and simulation calculation. Next, for energy balance, the heat flow calculated through simulation and manual has a difference of 32.945 kilojoules per hour, showing out an error percentage of 39.72%. From the result above, we found that separator is giving out heat to cool down the product from 100 to 87.07 Celsius degree. So the possible explanation or the main factor that causes the error percentage occur is due to the assumption we made in the manual calculation had excluded the work done by the separator and also the elevation of the outlet flow. In fact, every separator in the industry has a different tank height. We eased our calculation with assuming the tank height was 0 so that there is no elevation of the outlet flow between the product and our unwanted product. Thus, it will resulting our value between the manual and simulation has error occur. So as recommendation, tank height and elevation of the outlet flow must take consideration in plant design and calculation. After that, we study for heat recovery analysis. We run through a simulation with recycle stream and without recycle stream to see the differences between these two simulations. The result was recorded in a table in the slide. First of all, the value for the heat duty of heater for these two simulations are the same because the heater was installed before the reactor and our recycle stream was installed after the heater. Second, for the heat duty of cooler 1 and cooler 2, we found that the differences between these two simulations are 2724.664 kilojoule per hour and 1170 and 365 kilojoule per hour. Thus, the overall heat duty for heater and the two cooler for these two simulations are 3895.028 kilojoule per hour. Furthermore, the simulation with recycle stream will increase our reactant, thus resulting our product NaOH to increase in the final outlet. So as you can see in the table, for simulation with recycle stream, our NaOH product have 0.399 kilomole per hour compared to simulation without recycle stream only have 0.3599 kilomole per hour. There was a differences of 0.04 kilomole per hour. So based on the result above, we found out that the overall heat duty with recycle stream is larger than without recycle stream. Our product NaOH also increased as well due to recycling the reactant will promote more reaction occur as more unreacted reactant run through reaction again. This phenomena can be explained with the equation Q equal to mc delta T as we recycling the reactant into the reactor so that the total mass flow into the reactor is greater. Hence, more energy is required to cool down the product at outlet, thus resulting our overall heat duty to increase for the simulation with recycle stream. Finally, recycle stream will increase the inlet mass flow, causing more reactant into the reactor, therefore our product will increase. So in conclusion, the plant design has achieved the objective of this study case. With the aid of Unisim, the plant simulation designed by us was able to produce 100 metric ton per year of NaOH. A graph of NaOH product in the final stream S13 versus mass inflow in the initial S01 stream was plotted below, and conversion 100 metric ton per year into 11.416 kg per hour was also carried out. So the inlet mass flow rate chosen in our simulation is 133.3 kg per hour, was able to achieve the desired production of 100 metric ton of NaOH. The recommendation inlet for the plant can be chosen from 130 kg per hour to 138 kg per hour to produce at least 100 metric ton per year. Okay, that's all from our presentation. Thank you, Mr. Fauzi, for teaching us this subject. Thank you, and the end.